hey, and somebody will say, no, 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 I can hear some sound directly come from my mouth. So that is not same as what you explain. Of course, when I come to you and you hear something directly come from me and some due to reflection. Oh, that's the topic we are going to study in room acoustics. Okay, first I can argue that energy, sound energy, in the room, average the energy in the room would be integration, and I am integrating this volume, delta V, okay, 1 over delta V, oh sorry, average it over the volume I had. Let me change this notation. This would be the averaged energy. Okay, averaged energy. This notation means average the energy at certain point R and time. So I denote that this is the position R. Okay? And this is volume. E R T dV, that is the volume average the energy. And then I summing up this during some time from T to T plus a delta T and average it. So that is the average the energy at position R with the volume delta V. That delta V is occupied, is generated by the sound during delta T, and the delta T would be larger than the period of typical wavelengths. Okay? So for instance, when I typical wavelength would be 34 centimeter, and therefore the volume would be 34 larger than 34 centimeter multiply and take a cube, that would be the volume. Okay, and I am averaging it over the period of wavelengths lambda 34.3 centimeter. Okay? And this average the energy then follow the following proportionality. That is, okay, I have energy reverberant. That means the sound that has many reflections, okay, integrated over the volume. That is the energy over here. And the rate of change, this energy, in other words, if you measure the sound energy in this volume, and of course the energy in this volume would be changing, right? It's changing. Huh? And that has to be balanced by what? Something power in. Right? Something power in. But if this volume is fairly large, like the entire volume, then I can say that this rate of change of energy has to be balanced by power in, meaning that the sound coming into the room, but I could only say minus power out. That means when I shout over here, the rate of energy increased inside of the volume would be balanced by how much energy is coming out per unit time. Right? If there's no energy coming out, then that has to be zero. That means this one has to be constant. That makes sense. Okay? That is simple. And then we could think that, hey, what would be the relation between power out and this energy? Or mathematically you could say that if I can find the relation between power pi out and the E reverb, then I can have an equation that is expressed by one dependent variable E, and that will be nice, right? So let us think that what is the relation between power out and the energy? Okay. And the dimension has to be same if we use the equal sign, right? Dimension has to be same, right? And this dimension is not same. So I could say again, that is the, what is it? That is the energy density inside of the volume. So if I multiply V over there, then that is the total energy inside of a volume. In other words, rate of change of total energy inside of the volume is going to be balanced by how much energy is coming out per unit time. That's simple, right? Or you could say this holds if simply say the sound field inside of volume is completely diffuse. Right? Then total integration would be this is constant with respect to not time, with respect to space, volume. Therefore I can take it out this and then multiply simply V, and the V is constant, therefore I can get this. So physically we can get this, or mathematically we can get this from this equality, from this equality.